Hello everyone. So in part 7 of elimination reaction video, we will see a great deal of variety of elimination reactions. So first type is Hofmann degradation. So first we have to prepare our starting material for the elimination reaction because actual elimination is taking place in the third step and the fourth step. So first we will see how we can make our starting material for this degradation. So this molecule, you can see this is a secondary amine. Here we are using excess methyl iodide. So what is the purpose of using excess methyl iodide is that there is formation of this salt. So two methyl groups are attached, you can see, and next we are adding Ag2O in presence of H2O. So here I minus is replaced by HO minus. So in Ag2O and H2O, when we are using in the reaction medium, AgOH will be produced. Now the actual reaction is taking place. We are simply heating the molecule, and if you consider the hydrogen at this position, because this portion is actually our leaving group. So if you consider this is as alpha carbon, this will be beta carbon. And for your convenience, suppose this is number 1 and this carbon is number 6. So after the reaction, this is 1 and this is 6. So this hydrogen, it will be removed and this carbon nitrogen bond will be broken and nitrogen will be now neutral. So this is the first elimination that is taking place, and again we are using the same sequence of reactions. That is the first step, which is excess methyl iodide. In the second step, Ag2O silver oxide in presence of water, and the third step is heat. So if you do all these steps sequentially, then finally you will get another elimination. Fine. So if you are considering this is as leaving group, because it will be converted in the leaving group by using this methyl iodide and Ag2O, it will be NMe3 and HO minus as counter ion. And there will be positive charge over nitrogen. So if this is alpha carbon, this is beta carbon. So the hydrogen from the beta carbon, it will be removed. And this is the leaving group, finally removed. Okay. So this is our final product. So two elimination reactions are actually taking place. So this is the first type. Now come to the second type, which is 1,3 gamma elimination reaction. Though these are not very common, but still we should know how it is taking place. So here you can see our our leaving group, which is trimethyl ammonium salt, and I minus is the counter ion. We are using very strong base sodium amide in presence of liquid ammonia. Now this is alpha carbon, this is beta carbon, and this is gamma carbon. So the hydrogen from this carbon, it will be removed actually, and there will be formation of this gamma carbon and alpha carbon bond, and finally you will get this molecule. Now if you one question may arise in your mind, that why the hydrogen from this beta position, which is the most common, that is 1,2 elimination, why this is not taking place? The reason behind that, when this CH bond will be removed, there will be some negative charge generation. If it is E1CP, that is fully developed negative charge. Suppose if it is E2, then it is partial negative charge. But still, whether it is partial negative charge or full negative charge, phenyl group is just beside that. So this negative charge can take part in conjugation with the pH ring, with the phenyl ring. So that is the driving force. But if you are removing this hydrogen, there is no such group just present just beside it so that the resonance can take place. So that is the driving force that we are getting gamma elimination. Okay. Next type is debromination of vicinal dibromide. Now most of the examples of elimination, we have seen that this is removal of hydrogen at some leaving group. But here this is to some extent different, because here two bromine atoms are actually removed. Fine. So we are using vicinal dibromide, that is two bromine atoms are present at 1 and 2 carbon. So this type of molecules, these are known as vicinal dibromides. So basically two bromine atoms are removed in this molecule. Now for this type of reactions, you have to use some reducing agent, it may be iodide ion. So here we are using sodium iodide. You can also use zinc. Fine. So I minus, first it is attacking this Br. So C-Br bond will be broken, and then this C-Br bond is broken. So obviously this is our main product. But what are the byproducts? See, this is the interhalogen IBr and Br minus that is also produced. Another example we will see, which is cyclohexane derivative. These two bromine, these are already in anti position. In the first molecule also the two bromine atoms are in anti arrangement. So this is stereospecific and goes through an anti pathway. So here also we use some reducing agent. Suppose you are using ZnBr, so it will attack this Br, and finally we are getting a new CC bond. So this is the third type, that is debromination of vicinal dibromides. Next type is dehydration of alcohol. Now this is very common. This type of reactions are favored by high temperature, and unlike other eliminations where mostly we use base, here it is catalyzed by different types of acids. Not just acids, PBr3 SOCl2, that also we can use. Now for 2 degree and 3 degree, E1 mechanism operates, and in case of primary, E2 mechanism operates. Okay. Now why for 2 degree and 3 degree E1? Because of the stability of carbon ion, which is not possible in case of 1 degree. So this molecule, it is tertiary butyl alcohol. So first you can see the water molecule, it is in protonated form. So the lone pair over oxygen, it is taking one of the proton. You are getting a neutral water molecule. Now this CO bond will be removed and you will get a carbocation intermediate. That is E1 mechanism. And finally, one of the beta hydrogen, it will be removed and you will get a new CC bond at this position. Okay, this is the final molecule. Next we will see another mechanism which is going through E2 mechanism. So this molecule is 1 degree. So in this case also, first this OH is protonated, there is positive charge over oxygen, and see the here A is actually it is produced from here. When the lone pair over oxygen, it will abstract this hydrogen, A minus will be generated. So this is nothing but HO. So this HO it minus, it is abstracting the proton, and all these bond breaking, all are going on simultaneously. This bond breaking, this bond making, then again the breaking of this bond. So all are going on, and this is the transition state is not shown here, but this is the process, and finally we are getting our alkene. Okay. So next, now another example of dehydration of alcohol we have here, but this is catalyzed by metal oxides. So metal oxides can also be used in case of dehydration of alcohol, and different products will be formed depending on what type of metal oxides you are using. Here we are not going into the detailed mechanism that why when you are using aluminium oxide you are getting one type of product, and thorium oxide why you are getting another type. Not just another type, I am talking about different type of residue isomer that may vary. So in case of Al2O3 you are getting this isomer, that is the most substituted alkene, that you are getting 90%, but less substituted you are getting 10%. But when it is thorium oxide, you are getting the less substituted as major. So depending on your requirement, whether you want the terminal alkene or the less substituted alkene as your major product, then you have to use thorium oxide, and if opposite is the case, you have to use aluminium oxide. So it depends on what type of metal oxides we are using. So dehydration of alcohol, here we are not using any base, we are using different types of metal oxides at catalyst, or we can use here you can see H2PO4, H2SO4, PBr3 or SOCl2. All these can also be used. Okay. Next we will see pyrolytic scene elimination, or you can also call it elimination internal or intramolecular elimination. Different names are there. So for some substrate, until now we have seen most of the time we are using base in case of elimination. And in the last example you have seen we are using some acid catalyst or metal oxides as catalyst. But there are some substrate where you do not require any external agents for the elimination to take place. So here simply heating is enough. You just have to heat the substrate. Now it is taking place in a concerted manner via cyclic transition state. And why it is intramolecular or internal? Because there is intramolecular proton transfer is taking place, and it is taking place through scene elimination pathway. So what are the examples? Now this pyrolytic scene elimination, it is specific for some starting material. It doesn't occur just for any substrate. There is some specific substrate for it. So what are the substrate? Esters, xanthates, amino oxides, sulfoxides or selenoxides. Now depending on what type of substrate you are using, there may be different types of name for the reaction, but actually all of them are pyrolysis. So when it is amine oxide, see the name is scope elimination. And when it is sulfoxide pyrolysis, it is known as, there is no specific name, but here the substituent you can see. This portion is common for all the molecules, only there is different at this portion, right? There is a plus charge over selenium. So when it is xanthate, then we see there is RsC double bond SO. When it is selenoxide pyrolysis, this is the molecule. And another thing I want to mention that when it is xanthate, the name is Chugev elimination. There is a special name for the reaction which is Chugev. Okay. Now see, in most of the cases high temperatures are required, right? And these two special cases, you see the temperature is comparatively higher. If you compare with the first three, the last two, the temperature is high. Now the last two is these two, that is esters and xanthates. Here your cyclic transition state, it is involving total 6 atoms. 1, 2, 3, 4, 5, 6. Here also total 6. But the first two, if you accept the first two, in the later 3 cases you will see all these are 5 membered, isn't it? So that is the only difference. And here I have written all the molecules in orange color, which is the byproduct of the elimination, because this alkene is common, which you will get from all these 5 substrate, but these are the byproducts. Now why in case of the last two, that is ester and xanthate, that is in the box, the first 2 examples, why we are requiring higher temperature? The reason is that esters and xanthates, why they require high temperature? Because of the stronger CO bond. You see, this CO bond is present, which is not present in case of the next 3 examples, right? And also the lower polarity of the CO bond or CS bond. That is, just focus on this part. So because of this reason, we have to provide more temperature compared to the other 3 substrates. And now just compare these two, ester and xanthate. In case of ester, the temperature is comparatively high with respect to the xanthate, isn't it? So why it is so? Because of the favorable bond energy change from OC double bond S. So if you look at xanthate, before the reaction it is OC single bond and then C sulfur double bond. And now it is changing to CS single bond and CO double bond. So this is favorable. That is, from CS double bond, now you are getting CO double bond, which is favorable bond energy change. So as it is favorable process, so that is why in case of xanthate, you are providing lower temperature. compared to the ester. Next we will see some examples of pyrolytic elimination. And why I have chosen this example, here we can see the importance of cis alignment of the eliminating group. So this is ester, right? Ester is eligible for pyrolytic scene elimination, and as the methyl group here you can see it is above the plane, so the hydrogen, it is below the plane. Now this hydrogen is to be removed by pyrolytic scene elimination. We are providing high temperature, and as this hydrogen and OCO-CH3 group, these two groups are in scene arrangement, so that is why the cis isomer, sorry, cis, it is not actually cis isomer, it is trans isomer. Why it is trans? Because we are focusing on these two groups, the methyl group and the acetate group, both are opposite sides, so that is why it is trans isomer. But so you are getting the reaction very easily actually. But if it is a cis isomer, suppose the methyl, if it is below the plane and this hydrogen now above the plane, now they cannot have the scene alignment, and obviously pyrolytic elimination, the requirement will not be fulfilled. That is the both the departing group must be seen to each other. That requirement will not be fulfilled in case of cis isomer, so that is why it requires a much higher temperature for elimination. So trans compared to the cis isomer, it will be favorable for pyrolytic scene elimination. So this is the example of ester pyrolysis. In the next example, we will see we are getting E versus Z product, and the E product is measured. First we have to prepare our substrate, which is amine oxide. So for that we are using hydrogen peroxide H2O2 with this substrate. This is the molecule that is given, but first we have to make the amine oxide. So when we are making the amine oxide, if I put number over these carbons, suppose the carbon which is carrying the NME2 group, that is 1. So this will be our 1 carbon, this will be 2. This is 1 carbon, this is 2. Now two types of arrangement may be possible. With the 1 carbon, there is a NME2O- group, there is a ethyl group and hydrogen, and with that 2 carbon you can see there are 2 hydrogens and 1 methyl group. Now this is one arrangement where this group and the hydrogen which is to be removed, both are in scene arrangement, in scene geometry. But the another arrangement that is possible, just rotate this carbon, that is the carbon 2. So if you rotate this carbon, now this is another arrangement, but in this arrangement what is the problem? There will be static repulsion between this ethyl group and this methyl group. So obviously this transition state will be less favorable energetically compared to the first one. So here also scene arrangement is present between the two departing groups, but the problem is here, static problem. So that is the reason that why we are getting 71% as Z product, which we are getting from the first geometry, but we are getting 29% of the Z product. So here we are getting the E product maximum. Okay. So here it is E product because methyl group and ethyl group both are opposite to each other, but in the second arrangement both are on the same side. So this is example of Cope elimination. Another example of ester pyrolysis. So here what is significant is that from the thioisomer you are getting E stilbene, but from the erythroisomer you are getting another product. So first we will see the molecule, though I have written the molecule, these two, but another arrangement that also you can see. Okay, though both are same. The picture that is drawn in the box, that is sawhorse. So this is actually the thioisomer. Okay, so in the thioisomer, why we are calling it thio? Because pH and H, they are on the same side. That is, both the pH group, they are trans to each other. See, this pH group and this pH group. So this is a thioisomer, but The erythroisomer, both the pH group, they are on the same side. This is the erythro. So in that arrangement, OAC and deuterium, they are on the same side. And here also OAC and deuterium, they are on the same side. Okay. So this is the trio and the second one is erythro. But why we are getting different types of product? The reason behind that is, in the first case, this deuterium and OAC, these two are removed. And you are getting the new bond here. Okay. And in the second case, now, if you rotate this bond, now hydrogen will be in syn position with this OAC group. So if here now this CH bond is broken and this OAC group is removed, you are getting a new bond here. Fine. So that is why we are getting E1 deuteriostilbene. That is the deuterium substituent is already present in the alkene. This is also stilbene. This is a actual stilbene, and this is a derivative of stilbene where deuterium is also present. Now one question may arise here, that why we are rotating this bond? Why we are not simply removing the deuterium and OAC? But if you do so, the molecule that you will get is, both the pH are on the same side. This molecule you should get, but we are actually not getting it. We are getting this product. So why we are not getting it? Because in the transition state, both the pH group, they are on the same side. So from the energetically, if you consider this thing from energetic point of view, then obviously this is less stable. So that is the reason first we are rotating this carbon, and now this hydrogen, it is in syn arrangement with the OAC, and that is why we are getting this. We are not getting this molecule. Okay. So that is all about this problem, that why from the trio we are getting E-stilbene and from the erythro we are getting E1 deuteriostilbene, but we are never getting C-stilbene. Fine. So in the next video I will discuss some problems regarding elimination, where we not just elimination, we will also see some substitution is also there is some competition between substitution and elimination. So regarding that I'll discuss some problem in the next video. And if you are finding this video very helpful, please like, share and subscribe. I'll see you in the next video. Until then, goodbye and thank you for your time.